right, so we have the last paper, and the presenter is Chongyun Park from UNIST, and the title is Efficient Use of the Free Prevention with Opportunistic Page Level Sweeping. All right, you can start.
Thank you. Hello, my name is Chongyun Park from UNIST. Today, I will briefly introduce our work on UGF-free mitigation. UGF-free is still prevalent. You can see the data from MVD. The number of UGF-free vulnerabilities is increasing every year. UGF-free is a bug where a program uses a pointer to the previously freed heap chunk. If this is the case, an attacker controlling the freed chunk can manipulate the program's behavior. Here, we have a program invoking a function using a function pointer. Object A, which has a function pointer, can be freed and reallocated to object B. If the problematic part of this program is where the program executes a function pointer to object B without any additional safety checks. And if malicious modifications occur to the object B by accessing the dangling pointer object A before the reallocation, then the program may be tricked to execute a shell for an attacker. The importance of mitigating UGF-free motivated many works on the problem with different assumptions. While each has its own strengths, we only focused on the two existing approaches that do not need any special hardware and recompilation. First one is garbage collect-like approach called mark and sweep allocator. Second is one-time allocation approach called FFMLO. Let me talk about the details. The basic idea of garbage collect-like approach is to delay the allocations and insert unsafe objects into the current list. Those objects are used when they are found to be safe to use after the procedure called mark and sweep operation. Marker determines if each chunk can be safely used or not by memory scanning. And to verify the dangling pointer existence correctly, the application process is stopped while the marker thread runs. We call this stopped period or stopped word. Subsequently, sweeper traverses the current list and inserts safe object into the free list. Eventually, we can reuse objects safely after mark and sweep operations. However, existing garbage collector-like approaches suffer from the significant overhead on execution time for allocation-intensive benchmarks. The interesting part of this result, the one-time allocation approach does not suffer from the allocation-intensive benchmarks. To find the root cause of characteristics, we implemented delayed reuse, which simply delay the allocations and reallocate them without any safety checks. The reason why we implemented delayed reuse is to analyze the impact of delaying free of mark and sweep allocator. We conjectured that delaying the reuse of freed chunks makes an allocator allocate either fresh chunks or reused chunks from a while ago, resulting in lower spatial locality among temporary local allocations. So we measured and determined the individual distance based on the difference between the base addresses of two temporary local allocations. So we measured the average distance between the allocation and the 10 nearest chunks that are allocated before and after the allocation. As expected, the delayed reuse has high average distance, meaning low spatial locality, and incur considerable overhead on execution time even without any safety checks. While FFmpeg has low average distance, meaning high spatial locality, and incur much less overhead on execution time. The reason why FFmpeg has high spatial locality is that FFmpeg always allocates fresh chunks from the top chunks. Because FFmpeg does not use virtual address space, so it expands the heap high and allocates fresh memory from the top chunks. This strategy of FFmpeg increases the spatial locality among temporary local allocations. To implement a better mark and sweep allocator that does not suffer from significant overhead for allocation-intensive benchmarks, we decided to implement FFmpeg as an underlying allocator. So we suggest HushVac as a mark and sweep allocator having allocation strategies of FFmpeg to reduce the significant overhead on execution time for allocation-intensive benchmarks, and we also modified FFmpeg to a mark and sweep allocator to support indefinite applications. To combine two different approaches, we reuse virtual address space. Existing garbage collector-like approaches delays the reuse of physical memory, but HushVac does not. If there are fully deallocated pages, HushVac remap those pages to release physical memory, and HushVac delays the reuse of virtual pages and reuse them after mark and sweep operation. To efficiently reuse virtual address space, we made two design decisions. First, it's okay to use virtual pages opportunistically, unlike garbage collector-like approaches. Existing garbage collector-like approaches suffer from memory pressure due to the long current list and the physical memory chunks in it. On the contrary, HushVac does not waste the physical memory, so HushVac can do mark and sweep operation opportunistically. And in terms of the spatial locality among temporary local allocations, delaying the reuse of virtual address space does not lower the spatial locality among temporary local allocations. Moreover, this design helps to reduce stopped order time that increase the overall execution time in the garbage collector-like approaches. Second design, it's okay to reuse at page level rather than as a batch of pages, unlike one-time allocator. Existing one-time allocator split VMA to release physical memory because it calls unmapped system calls. For this reason, FFmpeg should have released physical pages in large batches to avoid creating many fragments of VMA, which potentially increase memory consumption. Unlike one-time allocator approach, HushVac remap fully deallocated pages to keep the virtual address space and release the corresponding physical pages without splitting VMA. So this design enables HushVac to release physical pages in smaller batches, potentially at page level. Today, this paper presents many design choices that we made for HushVac. Among these, I will only explain about sub-page reuse because of the limited time. Existing one-time allocator approach has internal fragmentation problem by long-lived objects. Because FFmpeg does not reuse virtual address space, some long-lived objects prevent a page from being released. The interesting part of this talk is that HushVac is a mark and sweep allocator that can use memory chunks after mark and sweep operations. So we maintain a per-page free list inspired by mymalloc, and HushVac consumes the free list as much as possible. Moreover, HushVac reuses small chunks in the fragmented pages where allocation and deallocation occur, not to lower the spatial locality among temporary local allocations. For evaluation, HushVac uses one mark and sweep thread and 10 marker thread. The baseline is glibc. In allocation intensive benchmarks on SPEC 2006, you can see HushVac is faster than markers and has lower memory usage than ffmalloc. In overall average performance on SPEC 2006, HushVac also is faster than markers and has lower memory usage than ffmalloc. However, HushVac has two limitations. First, HushVac has higher execution time overhead than ffmalloc. The reason is that frequent remap system calls incur performance overhead. And the second limitation is that HushVac does not solve the ffmalloc's internal fragmentation problem. The reason is that even though HushVac reuses small chunks after mark and sweep operations, it is impossible to fully and safely reuse every page. Here is the conclusion of this talk. We found the root cause of overhead in garbage collector-like approaches. The spatial locality potentially affects the performance overhead, and simply delaying the reuse fresh chunk affects the spatial locality among temporary local allocations. So we decided to use ffmalloc as an underlying allocator, and we implemented HushVac as a mark and sweep allocator to support indefinite application and reduce the significant overhead for allocation intensive benchmarks in garbage collector-like approaches. To combine two different approaches, HushVac also serves several design choices, leads several benefits. First, allocations are aware of the spatial locality, and HushVac reduced performance overhead in garbage collector-like approaches, and HushVac improved the ffmalloc by reusing virtual address space. Thank you for listening to this talk. Do you have any questions?
Yes, any questions?
Hi, I just want to clarify the evaluation. So the cost of HushVac will depend on the frequency of mark and sweep, right?
Right.
Right. So the evaluation, did you vary that as a parameter?
This one?
Right. So it's not possible to tell the overhead because it depends on the frequency of mark and sweep and also the size of the live heap.
The reason why we did not attach the overhead from the mark and sweep operation is that our HushVac do mark and sweep operation opportunistically because we does not delay the physical memory. So the average performance of mark and sweep operation on SPEC 2006 almost 3 seconds. So you can see the details about the Mark-and-serve operation latency in the papers. We attached every benchmark's stop the world execution time overhead in the paper.
Okay, we can take it offline.
All right, any other question? Okay, if no, I think that's all for this session. Thank you for coming, and thank the speaker again.